So we ended the last lecture with the principal normal strains in terms of the principal normal stresses, and that was the Hooke's law using those principal stresses and strains. So if I write that here, we can say strain 1, principal strain 1 over E times sigma 1 minus nu times sigma 2 plus sigma 3. And then the same thing for the second principal normal strain and the third principal normal strain. But instead of sigma 1, we would have sigma 2, sigma 3, sigma 1, and sigma 2. And everything else kind of remains the same. Okay? So this is helpful. And if we have rotated our cube such that we only have principal stresses, then we can calculate these principal strains. Okay? The problem comes in if we need to look at the shear direction, right? So I said that we'd be looking a lot at the shear direction for failure criterion. So now let's think about a shear situation. And then that'll help us to get an overall strain due to normal stresses and shear. And then we can think about how that applies to a plastic deformation situation. Okay, so similar to strain in the x direction is equal to stress in the x direction divided by the elastic modulus. We can write expressions for shear strains. So we can say shear strain, and I'm going to write that as gamma xy is equal to the shear stress xy, tau xy, divided by g. Okay? And there is a long description in the book of how this is derived, and I'm going to skip that because I just want to get to useful equations, right, so that we can start solving some more problems. Okay? But I do want you to know generally where these things come from. And so we can say that from the shear stress on the x face in the y direction is related to a shear strain that causes the cube to shear in the direction that the shear stresses are going. And those two are related by a coefficient of g. With the analogy between the normal direction and the shear direction, the normal direction had the elastic modulus E, or the Young's modulus, and in this direction we have the bulk modulus G, and it's related to the elastic modulus, but it is not equal to the elastic modulus. And the relationship between them is G is equal to elastic modulus divided by 2 times 1 plus the Poisson ratio nu. Okay. So that's how we relate the difference in direction, incorporating the shear direction into this equation here. Okay.
Did
Yes?
you say that G was the bulk modulus?
Yes. Oh, that's the shear modulus. Had the wrong word in my head. Yes. That's why it's used in the shear stress strain relation. Yes, it's the shear modulus, not the bulk modulus. Sorry about that. Okay. So we can, in the same way as we have principal normal strains, we can also have principal shear strains. So I'll write those on the next slide. So principal shear strains. So that's going to be gamma 1, right? First principal shear strain is equal to plus minus the first principal shear stress, tau 1, divided by shear modulus, which is also equal to plus or minus the difference in the principal normal stresses divided by 2 times the shear modulus G. Okay. And we write a plus minus because of the directions of shear. If you think back, we talked about the principal normal strains, right? They go along the principal normal direction. So if we have our stress cube, those are associated with the directions of those normal faces. But when we calculate the principal shear stresses, those can be 2 different directions for any given normal strain or normal stress, right? They can go in an X across. And so that's why we have a plus minus here. Okay. And then the similar definition can be written down for the others. Oops, the first one should have a 1 up here on the top. It should be the maximum shear stress, which is tau 1, which is sigma 1 minus sigma 3. Nope, I lied. Oh my gosh, I gotta get my notes straight here. Sorry, give me 1 second. I wrote them out of order to try to help myself, and then I got messed up. Okay, so gamma 1, tau 1, sigma 2 minus sigma 3. Okay, gamma 2, tau 2, sigma 1 minus sigma 3. Okay, so these are just the book conventions for naming. Okay, so gamma 3, tau 3, and sigma 1 minus sigma 2 divided by 2g. Okay. Yes?
Can you explain why for tau 1 it's sigma 2 minus sigma 3, even though it would be larger if it was sigma 1 minus sigma 3?
Give me 1 second. Honestly, no. So I'd have to go back and look at the textbook of like why the nomenclature doesn't follow the same as the normal stresses. So 2, 3, 1, 3, 1, 2. No, I need to think about it a little bit more. I do not know the answer to that. Sorry about that. Okay. So these are some definitions, things we can calculate. And so if we know the principal normal strains, right, like E1, epsilon 1, epsilon 2, epsilon 3, and then gamma 1, gamma 2, gamma 3, right? We can think about the deformations that might happen at a particular location on a component if we know these parameters. Okay. However, it's because of the directions of them, I think, and even my confusion up here, it's better to go back and calculate them in the frame that you have and then sum them up, okay? So we calculated before, I made that table in the last lecture, and we had all of the strains that happen in the normal direction due to the whole deformation of the volume, right? And so now if we add in a shear component, then we have both of those. So I'm going to go back to x, y, z coordinates for a minute. And so let's say in the x direction, we had epsilon x And then it was the expression for Hooke's law. So I'm going to write that one more time. You're going to get tired of writing it. So sigma x minus nu sigma y plus sigma z. Okay. But then we also have, if this is on our stress cube, this is a strain along x only from a stress along x. But if we think about the cube and the other stresses that could be on it, we can also have a shear strain along x. So we would have gamma x, right? So gamma xy. Hang on, let me make sure I get this right. Nope, I'm going to change it. So we'll have a gamma of, let's say, gamma. Nope. All right, I had it right the first time. Okay, so we're going to say gamma xy. So that is the shear strain along x due to a stress, a shear stress in the y. And so we're going to say that that is tau xy divided by shear modulus. And then we'll also have shear stress z, nope, hang on a second, shear stress x due to z. And that's going to be tau xz divided by shear modulus. So if we want to go back to our cube and think about all of the shear strains that could exist, then you have to add together all of these terms. So if we have on our stress cube, we do have normal stresses applied, sigma x, sigma y, sigma z. And then we also have shear stresses applied in those directions. And we want to know the overall strain on this thing. We have to add together the strains from the normal stress plus the shear strains. All right. Okay. So that is the total strain in the x, y, and z directions. And that total strain can then be transformed into principal strains. Okay. But this is how it breaks back out in x, y, and z. And this can be done for each direction. Okay, so let's talk about using these kind of rules now to go into that plastic regime. Okay, and we'll talk about the comparisons with some rules that we might use that are like Hooke's law, but they're for the plastic regime, and how they compare, and then some useful equations for calculating these principal strains in plastic deformation. Okay. So we're going to switch gears a little bit. The book describes two ways of estimating the plastic strain, and one is kind of a subsidiary of the other one, so we're just going to consider the more simple one. So this is in the book, section 5.4. And the two theories are called the proportional deformation theory and the incremental strain theory. And the one we're going to focus on is the top one. Yeah. And so you look at the name, the proportional deformation theory, and we already have a lot of descriptions of stress and strain. Okay? And so what we're going to do is use that same formulation in the plastic regime. And so we're going to use a lot of the same assumptions. So we're going to explicitly state the assumption now that the volume does not change. So in plastic deformation, the volume of a specimen, the volume of our little stress cube does not change. Okay. We're also going to assume that there's no internal structural changes that are changing the direction of things. Okay? So that's our first assumption about volume. Our second assumption is that the principal strains, so I'm just going to call that like assumption 1, put a circle, assumption 2, principal strains remain parallel, so I'll just draw parallel lines, to the principal stresses. Okay. And so in the elastic regime, we had some variables like epsilon and sigma. And when we switch over to the plastic regime, we're going to use delta as our strain, our plastic strain, and we're going to use sigma prime as our plastic stress. So this assumption can be written as the first principal the true principal strain in plastic deformation is parallel to sigma prime 1, and the same thing for delta 2 and delta 3. So those remain parallel. And because they remain parallel, the corresponding values, this is our third assumption, is that the ratios of the principal shear strains to the shear stresses are equal at all stages. Okay, so I'm just going to write that on the next slide. So the third assumption is that the ratios of principal shear strains so that's those gammas that we talked about, and the corresponding principal shear stresses, tau, are equal, instantaneously equal at any stage of plastic deformation. So the way, and this becomes critical, this is how we're going to relate these two things. So this is the definitions that we have. So one of the principal shear strains was defined like this, delta 1 minus delta 2. And so if we take the ratio of that to the corresponding shear stress, then that ratio is equal to the other ones. Give me 1 second. Okay. So I'm going to write out the other combinations here. 2, 3, 2, 3, and 3, 1, 3, 1. And the ratio of those is going to be, we're going to call it some capital CI. That's a constant. Okay. We're also going to assume that the strain that we calculate for plasticity is much higher than anything we would calculate as elastic strain. So usually those stress strain curves were on like a log scale, right? And so if we're in this region here, our strains are going to be much larger than in the elastic regime. So we're going to say that the elastic strain is negligible compared to plastic strain. Okay. And then the last assumption is that plastic flow, or let's say plastic deformation, can only happen for increasing loads. So basically, the absolute value of the applied stresses has to be going up, right? So I guess that would be like the rate, is greater than 0. So loads are increasing. If the loads are decreasing, if we are releasing our sample, then we only have elastic deformation. Let me write that the other way. So this is the same as we had with our stress strain curves at the beginning. So if we have decreasing loads, then we only have elastic deformation. And then Hooke's law holds for that. All right. So this is kind of the background of this proportional deformation theory. So let's talk about a cube now, or let's say a parallelepiped. The book doesn't say it's a cube. A parallelepiped that is undergoing plastic deformation instead of elastic deformation. Okay. So if I draw something that's not necessarily a cube, but is a parallelepiped now, and I can give it dimensions A, B, and C along, let's say, the X, Y, and Z dimensions we had before. So we can call that A, B, and C. And the volume of this parallelepiped now is just the product of those sides. Okay? So let's just start with that. And we'll say that the parallelepiped is going to be strained. Okay? So along the A direction, so along A, let's say that it's strained to epsilon 1, okay, in that direction. And, sorry, along A. Along B, it's going to be strained epsilon 2, and along C, it's going to be strained epsilon 3. Okay. So these are normal strains, so they could be pushing in, they could be pulling out, right? As long as they're increasing, or it's being loaded. So then the dimensions now of the deformed dimensions with those strains are going to be A times 1 plus strain along that direction, and the other side length will be 1 plus epsilon 2 and 1 plus epsilon 3. And if we multiply those together, we'll get the deformed volume. So let's call that the sheared, well, let me say the strained condition. VS is what they call it in the book. Strained condition, strained volume. If I multiply all them together, I come out with ABC at the beginning, and then the principal strain terms. So we can say our sheared, I ran out of space here, but our sheared volume, our strained volume is our initial volume times the product of 1 plus those strains. Okay, so I'll write that on the next slide here. So strained volume is the initial volume times the product of 1 plus those strains. Okay. But we had our first assumption, if you look back up in your notes, that said the volume doesn't change. So if we have our strained volume and our unstrained volume, those are equal to each other, then these three terms on the right have to equal 1. So 1 plus epsilon 2, 1 plus epsilon 3, those have to equal 1, because we just say that Vs is equal to V naught, and then those cancel out. We are going to go back to our definition now of true, come on, pen, true strain. Okay. And we're going to say that our true plastic strain now is that delta so true plastic strain is going to be delta, and let's say that it's the same definition that we had between engineering stress and engineering strain before. And now it's not elastic, it's plastic, but we'll use the same formulation. So we have the true plastic strain delta is the natural log of 1 plus the engineering strain. And that 1 plus engineering strain is exactly what we have in our volume definition above. And so we can say that our, if we take the natural log of both sides and then substitute this in, then we get the equation of our first sort of principal plastic true strain. And then if we take the natural log, we add whatever was a product before, plus plastic strain in the second direction, plus the third is equal to 0. So all the plastic strains in all three principal directions have to add up to 0. And that makes sense if we go back and think about just the elastic situation. If you pull in one direction uniaxially, the other directions have to contract. So the strains have to add up such that the volume is conserved. Okay. So we're going to use this, and we're going to plug it back in to that definition we had before, or sorry, the assumption we had before, that third assumption where those ratios were equal to a constant. Okay. So if we go back there, we had, for example, delta 1 minus delta 2 divided by sigma 1 prime minus sigma 2 prime was equal to some constant c sub I. And it was the same for the other ratios in the other directions. So we can rearrange that and write sigma 1 prime minus sigma 2 prime times the constant is equal to the difference of the principal shear strains. Sorry, principal plastic strains. Okay. And then if we solve these things together, so let me change colors here. So if we solve this equation where they add up to 0, and the equations, the rearranged from assumption number 3, I think it was assumption 3, yeah. And that all occur in the same two variables, we come up with some expressions that match sort of our Hooke's law. Okay, so I'm going to write those on the next slide. So we get delta 1 is equal to 2 times this constant c sub I divided by 3. We get our sigma 1 prime minus 1/2 sigma 2 prime plus sigma 3 prime. Close that up. And we can do the same for the other combinations. And they all have the same coefficient out front and the same coefficient inside. Okay, so if we go back and look at our Hooke's law, right, we had, recall, I'll just write it on here, first principal normal strain was 1 divided by Young's modulus, and then we had our first principal shear stress, first principal normal stress, goodness sakes, the Poisson ratio, and then the second and third principal normal stresses like this. That was our Hooke's law for one direction. So you can see the commonalities between them. And instead of elastic stresses, we have plastic stresses. That doesn't change, so that doesn't matter. What changes is the constants out front. So in the elastic case, we had 1 divided by Young's modulus. Now we have 1 divided by 3 over 2 Ci. And then instead of a Poisson ratio here, we have this 1/2 term. So you can see that these equations simplify back to Hooke's law. So these plastic equations here, they simplify to Hooke's law. If we come up with a plastic modulus, if they call it a modulus of plasticity, so we'll say D is equal to 3 over 2 times that constant, and the Poisson ratio is equal to 1/2. So D is our instantaneous, I'm going to write it down here, instantaneous modulus of plasticity. So that's helpful. Okay, so now we have a formulation for that's similar to Hooke's law, but now it's for plasticity. So we're not limited to the elastic range, and we have some sort of other modulus that we'll put in, this D. Okay. Okay. So in order to use this, we need to have a combined stress state. Okay, so we're not going to talk about combined stress states just yet and failure theories, but we're going to use a combined stress state to solve some problems in plasticity here. If we want to calculate these delta 1, delta 2, delta 3, okay, and principal strains to see if we're going beyond the that linear strain regime into the nonlinear strain regime where there's excessive ductility. So we need these thresholds. So if we go into a combined stress theory, we'll derive this later, but the octahedral shear stress, shear stress theory says that there's a combined stress state that represents sort of the maximum effective stress at any particular location. So if I take my stress cube and I have all the principal stresses, but I want to distill that down into a single value, then we're going to say that the octahedral shear stress, let's call it tau naught, is going to be equal to 1/3 times a combination term of all of the principal stresses that we have. So it's going to be a combination of the square of the differences. So it's going to be all these sigma primes, the difference between the combinations, and you square each one, take the square root of it all, and then you get this tau naught, and we'll call that the octahedral shear stress. Okay. And corresponding to that, we can say that there is going to be a shear strain associated with it that has a coefficient out front of 2/3 instead of 1/3, and now it's the difference between the shear strains, these deltas, squared, and then summed. Oops, that should be a delta 1. Okay. So what we want to do is use these combinations with what we know from our formulation of those pseudo Hooke's laws to come up with what is CI? What is that constant? So it's not something that we can just look up on a table or something like that. So that's why we have to come up with a way to find it. Okay. So we're going to use these two in order to find that, because we can apply the same situation to this octahedral shear stress and then use our plasticity sort of Hooke's laws. And then we can equate them to come up with an expression for the C sub I in terms of our strain hardening. Let me look up one thing real quick. Okay. Yeah. So if we recall back from the prior lecture, we had an expression where we had a plastic stress which was related to a strength coefficient times delta, which is our plastic strain to some n, and that coefficient n. Okay? So what we're going to do is we're going to find C sub I as a function of this strain hardening coefficient. And then we'll be able to use, once we know C sub I, we can use let's call them stress-strain relations for plasticity. Okay, so that's our goal. All right, so how are we going to get there? What the book has us do is apply a uniaxial test case for these so that we can come up with a simple expression and then plug it back into the octahedral shear stress. Okay, so for the case of uniaxial tension, then sigma prime 1 is greater than 0, and sigma prime 2 is equal to sigma prime 3 is equal to 0. And so let's plug that into the octahedral shear stress, so that tau naught equation. So everything cancels out that doesn't have the sigma 1 prime. So we end up with 1/3 times square root of 2 times sigma prime 1 squared square root, which equals square root of 2 over 3 times sigma 1 prime. Okay, so that's easy. It's just a ratio between the two. And we can do the same for the shear strain, that gamma naught. Okay. And there's a lot of math that goes into it if we only have the delta 1 greater than 0, and we have delta 2 equal delta 3. Oh, sorry, hang on one second. Let me draw that correctly. Okay. So if we do the math on that, we have to substitute in some other things. So I'm just going to write down what it is. It's just the same kind of coefficient type relationship. But instead of square root 2 over 3, it's square root 2. Okay, so we come out with those. And then if we go back to where we had the ratios, hang on one second. our first descriptor of the stress-strain relation was like this: 2 times C1 divided by 3 sigma 1 prime plus 1/2 of the other terms. Right, and so now we can cross out the sigma 2, sigma 3, so these go away. And we are left with delta 1 is equal to 2ci thirds, that's our coefficient, times sigma 1 prime. So this is our stress-strain relation for uniaxial tension, but plastic deformation instead of elastic deformation. Okay. If we rearrange that, we can come up with this constant, C sub I, is equal to 3/2 times delta 1 divided by sigma prime 1. Okay, so this is directly like a stress-strain relationship. And now we're going to plug in what we had from up here so that we have everything. So we have something in terms of these principal stresses, the octahedral stresses. So Ci is going to be equal to 3/2, and then we'll plug in for delta 1, we'll plug in the first equation, so that's going to be gamma naught divided by square root 2. And then we'll also plug in what we had for, if we rearrange the top equation, so now we'll have our octahedral shear stress. So it's going to be 3 times tau naught divided by square root 2. And if we do kind of all that simplification, we come out with gamma naught divided by 2 times tau naught. So that is our Ci. Okay. So we're almost there, but this is not related to anything with n. So now we need to get back to our strain hardening, what we know from tensile tests. That's the value we know, and so we need to be able to plug that into here. Okay. So if we go back to the equation from our strain hardening. Let me go to the next slide, actually. So, whoops, don't have another slide. Give me 1 second. This is the last bit. I think we have about 4 minutes left. Let's put another slide here. Sorry, PowerPoint died. Okay, so we're back. So from our stress-strain curve, we can fit something like that. Okay? And so now let's plug that in, plug in what we have now into that. So instead of S prime, we're going to have something related to the octahedral shear stress. We had 3/2 tau naught. And instead of the, and then that is going to be equal to K. And then our delta is going to be the, I think it's going to be that delta 1. Lost the page here. Yes. So then we have gamma naught divided by square root 2 to the n power. So all we've done here is substitute in our plastic stress and our plastic strain using this sort of effective octahedral stresses and strains. And then we're going to rearrange it. So gamma naught is equal to square root 2 times 3 tau naught divide by square root 2 times that strength coefficient k, and all to the 1 over n since we solved for gamma naught. Recall from the just above, we had an expression for what is C sub I in terms of these. So I had gamma naught divided by 2 times tau naught. So now you can see how these are related, right? So they both have gamma naught and tau naught in them. So we're going to eliminate gamma naught because we don't care about that as much as tau naught. So eliminate gamma naught to come up with what is C sub I as a function of tau naught. Right, so that's what we come up with. And we get C sub I is equal to square root 2 over tau naught times 3 tau naught divided by square root 2 times k to the 1 over n over 2. Okay. Yeah. So this is what we came up with. So that's good. And this is for a uniaxial stress state, right? We said that sigma 2 prime, sigma 3 prime were 0. So, So that's not as helpful, right? But instead of using this, instead of this expression having sigma 1 prime, sigma 2 prime, sigma 3 prime, it has this octahedral shear stress, tau naught. Right? So if it works like this using tau naught, we can take the complicated expression for tau naught, the full expression for the octahedral shear stress, and we can substitute it into here to get a long expression for what is C sub I as a function of n, of course, but then also sigma 1 prime, sigma 2 prime, sigma 3 prime. So that's what we want. And then we can know the stress-strain relationships between them. So if you're looking at that and you're saying, I don't want to do that, octahedral shear stress has a bunch of differences of terms, then you square it, then you put it all together. Oh, we also have K in here, I forgot. We also have a strength coefficient K. And then I'm going to put all that back in, and then I'm going to put it into those quasi Hooke's law like expressions. It's just going to grow without bound. Like we're not going to be able to write it on one slide. I agree. So what the textbook does is it uses some simplifying ratios. Right? If you've done any non-dimensional analysis in the past, you know that that can be very helpful. And so we're going to define some constants of alpha and beta, because I guess we can only use the first 3 letters of the Greek alphabet in the first few chapters of the book. So we're going to say that alpha is equal to sigma 2 prime divided by sigma 1 prime. And beta is going to be the same, but for sigma 3 prime, and everything's normalized by sigma 1 prime. Okay. So when we have these two expressions, and this is my last sort of minute here, I think we're going a minute over, is that we can come up with expressions as a function of alpha, beta, k, and n. So now we get, we can do delta 1, and we had an expression before that had c in there, but we don't know what c is, so now we do. So now we have delta 1 is a function of the stress-strain curve, which had k and n, sigma 1 prime, because we can't quite get rid of that one, and then our alpha and our beta. And those are going to characterize each one. Okay? And so we can say the same thing for delta 2. Come on. Delta 2 and delta 3. Okay. So I'm going to end there today. And what we're going to do for the first problem set, which I haven't released yet, apologies, is we're going to put some numbers to this. So I know it's been like 2 hours of sort of these conceptual things, right? How we're going to relate plastic stress and strain to elastic stress and strain. And, you know, it's like, where are we even going with this? You know, all the subscripts are difficult. We're losing track of things. But Let's put some numbers to it, and let's compare some different conditions so we can figure out what it means and get some better intuition. All right? So I can take a question. I don't know how long the lecture's allowed to go, but sure.
On the last slide, not the second to last slide, I guess, it had CI, and when you plug that in, where did that extra 2 go? Like gamma naught over 2 tau naught?
So the question is, where did this 2 go? If I circle that 2 right there, where did that 2 go? I don't know the answer to that. I think it went... Gamma naught was on the other side. I'm not sure. C sub I 1 over n. I think it went the way of me forgetting to write it down. So if I look at my expressions in my notes here, there is a 2 there. So,
Thank you.
yes, good catch. Okay, other catches. I know there will be other catches on the slides. Just put a message on the discussion board or let me know if you're here in class, and everybody can be on the same page. So thanks for going along with me. If anybody asks you how you're analyzing plastic strain, at least now you have some answer. All right. See you next week.